Hi, everybody. So we have day one today of 413. We're going to talk for 2 days about this section. Let's see. Um, we're going to talk about dependent, what the difference is between dependent and independent events. And today we'll be kind of focused on algebra and different types of problems to determine if events are independent or dependent. And then tomorrow we'll actually go back and we'll revisit those types of word problems where we used a formula and with the addition rule yesterday. Okay. Okay, so the warm up, I'm just going to kind of start you with it and then have you pause it and then work through it. It says some cars in a school parking lot have the following license plate identifications listed below. One of the license plates is chosen at random. Consider the following events. Okay, so we have the event V, which is the chosen license plate has at least one vowel. So we kind of go through and highlight or underline, circle, whatever you need to do to identify at least one vowel. So notice MRB, no vowels, KXL, this one has at least one vowel. This one has at least one vowel. Let's see, BCF, this one has at least one vowel. And then this one has at least one vowel. Okay, remember your vowels are A, E, I, O, U. All right, then let's see. I'm going to underline this. The sum of the digits on the chosen license plate is greater than 20. So I'm just going to kind of add up first. So this is 10, 11, this would be 17, this would be 8, 15, 22. Let's see, this is 13, and 10 makes 23. This would be 10, and 5 makes 15. This would be 8, and 8 makes 16. This would be 7, and 6 makes 13, and 5 makes 18. This would be 12, 22. Okay, so license plate is greater than 20. So let's see, that would be this one. So I'm going to circle this. So greater than 20, greater than 20, and greater than 20. Okay. So go ahead and fill out the Venn diagram. And make sure you label one circle as V and one circle as S and place these in the right place and then answer the questions. Okay, so go ahead and pause and then complete the warm up. All right, assuming you have finished and you're checking your answer, let's check and see what you got. So event V and S, it does not matter which circle you label. I would just do whatever one is first. So I've labeled this one as V and this one as S. So based off of, there's two up here that were just highlighted. Notice they're right here. There was just this one that was circled, so there's one that's just S. And then there was two of them that were both, so notice those are in the middle. And then there was two of them right here that were neither, which is why they're on the outside. Okay, where they go doesn't matter as long as they're in that space of the box. Okay. And remember, you got to draw that box in. List the outcomes of the following, not V. Okay, so what I would do is this. I would say, well, V is this. So V represents this entire circle. And there's 4 in that entire circle. So then not V would be the other 3. So it'd be this one, and this one. Order does not matter, but here's all 3 of them. Notice that there's brackets around it. Okay. The next one, V and S, would be this space in here. That's the overlap of the 2, and there's 2 in there. Notice you have these 2 right there. Okay. All right, so moving on. Independent events. Independent events means that one event does not affect the probability of another event. And that's the really important part right here, does not. Okay, so go ahead and fill that in. One event does not affect the probability of another event. Okay, so independent events, just to give an example, would be like it's raining outside and I stubbed my toe. Those are independent events because it's raining outside did not cause me to stub my toe. Okay. Dependent events you could say are like, um, let's see, like it's cold outside and it's snowing. Because if it's warm outside, then it can't snow. They're not like totally dependent on one another because it could be too cold to snow, but it can't snow unless it's cold. So they're dependent on one another. Okay. Another way to think about dependent is like you guys are all dependent on your parents. You depend on your parents to feed you, to put a roof over your head, to get you to school, to get you your athletics, all the things, do your laundry, whatever it is. But you're dependent on them. Independent means that you're you would be on your own. One thing does not affect another. Okay, so we're gonna have our second formula here. Yesterday we talked about the addition rule. Today this is called the independence rule, and it's what we're going to do to check for independence. So it's the probability of A and B equals the probability of A times the probability of B. So we can use this to check for independence, and that's what we're going to do today. If this formula is not true, if the probability of A and B does not equal the probability of A times the probability of B, then the events would be dependent. Okay, so this formula allows us to check. So I'm going to write that off to the side. Allows us to check for independence. So if this is true, then events are independent. If it's not true, then they're dependent. That's what we're going to do today. Okay, and then this is important as we go through. For larger samples, allow a 1% leeway, and I'll talk about what that means. Okay, so let's go through the examples. Example 1 says Emma's class is studying probability by playing games or conducting probability experiments. Emma can choose one of 3 experiments. If she gets an outcome with all matching results, she wins the prize. Okay, so here's what's important. She wins if she gets all matching results. The experiments are rolling a pair of die. So let's see, we have rolling a pair of dice, tossing 3 coins, or spinning 2 spinners. Which experiment should Emma choose to have the best chance of winning a prize? So let's see, she has the dice, she has the coins, and she has the spinners. Okay, so she has the option of which one she wants to choose. She needs to get an outcome with all matching results in order to win. So she would want to pick the one with the best likelihood of getting all matching results. Okay, so in dice, all matching results means doubles. Okay, that would mean like a 1-1, a 2-2, 3-3, 4-4, 5-5, 6-6. So there's 6 matching results out of 36 possible outcomes. If you look at your dice sheet, there's 36. The reason that there's 36 is because there's 6 outcomes here and 6 outcomes here. And if you multiply 6 times 6, it's 36. Okay. For the coins, all matching results would mean I'm going to write this out here. It would mean that you would have to flip 3 times and get all heads, or you'd have to flip 3 times and get all tails. And again, 3 times because it said 3 up here. Okay, so that means that there's 2 possible ways out of, and we talked about this yesterday, 8 possible outcomes. The reason that there's 8 possible outcomes is because for this coin, you could get a heads and a tail, so 2 possible outcomes, 2 possible outcomes, 2 possible outcomes, and 2 times 2 times 2 is 8. So that'll help you figure out your total number of outcomes. Okay. Next, on the spinner, getting all matching results would be spinning a 1 and then spinning on the other one and getting a 1, spinning a 2 and then spinning on the other one and getting a 2, or spinning a 3 and then spinning the other one and also getting a 3. So there's 3 possible matching results, and it's out of, instead of writing out all the outcomes, there's 3 possibilities here, and there's 3 possibilities here, 1, 2, 3, 1, 2, 3, and 3 times 3 is 9. Okay, so if we simplify this, 6 over 36 is the same as 1/6. 2/8 is the same as 1/4. And 3/9 is the same as 1/3. Okay, so again, which experiment should Emma choose to have the best chance of winning? And if you have a calculator, let's actually get your calculator out. Okay, so if we use our calculator here, we have 1/6, we have 1/4, and we have 1/3. And we can see that our best chance of winning then is 1/3. So I'm just going to make a note here that says the spinner has the best chance. I don't need to write a huge long explanation because I have found all of the probabilities for each. I can see that that's my best. Okay, so go ahead and flip over to example 2. Example 2 says that Mrs. Tolan is teaching her students about probability. She has a bag of 6 marbles. 2 of them are red and 4 of them are purple. Okay, so I'm just going to write here 2 red, 4 purple, for a total of 6. Okay. She asked her students to conduct the following experiments. Experiment A is that she picks a random marble from the bag and then replaces it. It's important. And then picks a random marble from the bag again. Experiment B is that she picks a random marble from the bag, does not replace it, and then picks a random marble from the bag again. Okay. So if you can imagine that there's a bag of 6 marbles, and somebody picks a random marble out of the bag and then replaces it and then picks a random marble from the bag again. Okay, so imagine that just happened. If somebody picks a marble and places the marble back in the bag and then goes to pick another marble, the second marble is not influenced by the first marble because there was 6 marbles in there to start with. So if you put your first one back and then pick another one, there's still 6 marbles. So if you picked a red the first time, put it back, you have just as likely of a chance as picking red or purple the second time. So when this happens, when we replace it, this is called independent. So these are independent events. So meaning independent events. So meaning picking your second marble is independent of the first marble because it doesn't matter what you picked because there's still the same total in the bag. Okay. Whereas if you were to pick a marble and then you were to hold on to that marble and then go to pick a second marble, these are dependent events. Dependent events. And the reason that they're dependent is because whatever you pick on the first poll is going to influence the second poll. 1, because the total number has changed, and 2, because if you pick a red, now there's only 1 red left. Or if you pick a purple, now there's only 3 purples left. But more importantly, it changes the total, which means it changes the probability. So dependent. The second pick is dependent on the first pick. Okay. It says here for each experiment, determine whether getting a red on the first pick and getting a purple on the second pick are independent events. And notice that we just did this. Then determine the probability of each event. So we're going to determine the probability of event A since it's independent. So the formula was the probability of A and B equals the probability of A times the probability of B. Okay, and you can only use this formula if they are independent, which is why we can do it for experiment A, but we cannot for experiment B. Okay, so we're going to use the letters that they chose. So they said determine whether picking of whether getting a red on the first pick. So red first and getting a purple on the second pick. So purple second equals probability of red first times the probability of purple second. Okay, so then I can say that, then determine the probability. So the probability of this, so red first and purple second equals, so the probability of a red first means that there are 2 reds, so that would be that would be 2 out of 6 times purple second. There are 4 purples, so that would be 4, and the total is still 6 because again, remember that we picked one, we put it back. So it's 2 out of 6 times 4 out of 6. So 2 times 4 is 8, 6 times 6 is 36. If we simplify this, we can divide both of them by 4, and that would be 2 nines. So that would be the probability of picking a red first and purple second. And again, we cannot do it for experiment B. We can for experiment A because they're independent, and this is our independent rule. So it does not work if they're dependent. Okay, so moving on. Example 3, Chip tosses a coin 3 times. Consider the following events. So let's create our sample space. So we have heads, heads, heads. We have heads, heads, tails. We have heads, tails, heads. And we have heads, tails, tails. Okay, and knowing that there's 8 outcomes to start with means I know that as soon as I get 4 for heads, then I'm just going to change the letters to tails. So I could get tails, 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 heads, tails, heads, tails, or tails, heads, heads. Okay, so there's my total of 8 outcomes. It says consider the following events. You have A, oops, sorry. A is that the first toss is heads, B is that the second toss is heads, and C is that there's exactly 2 consecutive heads. For each of the following pairs of events, determine if the events are independent. Okay, so in order to determine if they're independent, we want to know if the probability of A and B equals the probability of A times the probability of B. Okay, so that's what we're trying to determine. Is that a true statement? We want to do it for events A and B, A and C, and B and C. So I'm going to write this out for each of them. That means if I want to determine if these 2 events are independent, I want to know if the probability of A and B equals the probability of A times the probability of B. Put a question mark. Okay, then I also want to know if the probability, let's choose color here. I also want to know if the probability of A and C is equal to the probability of A times the probability of C. Okay. Then I also want to know if the probability of B and C equals the probability of B times the probability of C. Okay, so notice that I need the probability of A, the probability of B, and then the probability of C. So I'm actually just going to go find these up here and label them. So what is the probability that the first toss is heads? Well, there's 4 of them, right? 1, 2, 3, 4. Okay, I'm going to erase this because I'm going to need this later. So 4 out of 8 total, which simplifies to 1/2. What is the probability that the second toss is heads? Well, let's see, the second toss is heads. So there's 1 here, 1 here, 1 here, and 1 here. So again, there's 4 out of 8, which is 1/2. Okay. What is the probability that there are exactly 2 consecutive heads? So exactly 2. So you cannot count this first one because that would be 3. So this one has 2 consecutive heads. This one does not. No, 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 and yes. So there's 2 out of 8, which equals 1/4. Okay, so now what I can do is I can just substitute in here. Let's see. Oh no. Okay, so I know that the probability of A is 1/2 times the probability of B I just also found is 1/2. And then I have to go find the probability of A and B. Remember, that means that both of these things need to happen at once. So what is the probability that the first toss is heads and the second toss is heads? Well, when I go back over here, let's see. The first and second toss are heads. So that would be 1, 2, no, 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 no. So I have 2 out of 8. Okay, so 2 out of 8 simplifies to 1/4, and 1/2 times 1/2, let's see, 1 times 1 is 1, 2 times 2 is 4. So is 1/4 equal to 1/4? Yes, so I put a check mark next to it. That means that because this is true, these are independent events. Independent means that one does not affect the other, which should make sense with a coin because if we look again at the events, the probability that the first toss is heads cannot affect that the second toss is heads. It's a coin. It doesn't know what you got the first time. Okay, so let's try again. In the next one, we know that, I'm going to fill in here, move this over. The probability of A we know is 1/2. The probability of C we already found is 1/4. And equals the probability of A and C. So now I want to know what the probability of both of these happening at the same time are. So that means I need a heads and there needs to be 2 consecutive heads. Okay, so the first toss needs to be heads and there needs to be 2 consecutive heads. So this one does not work because there's not 2 consecutive heads. This one works because there's a heads first and there's exactly 2 consecutive heads. And then nothing else works. This one has 2 consecutive heads, but the first toss is not heads. So there's only 1 out of 8. If we multiply the right side, we're going to get that 1/8 equals 1 times 1 is 1, 2 times 4 is 8. This is true, which means that these are independent events. Okay, and that's what we're trying to determine. Okay, and again, that should make sense too, that they're independent, that one does not affect the other, because the first toss being heads doesn't affect the fact that there are 2 consecutive heads, because I can get 2 consecutive heads here. There doesn't have to be a heads first. Okay, so let's try the next one. The probability of B is 1/2. The probability of C is 1/4. And then I need to figure out what the probability of B and C are. So I need to know what the probability of both of these happening at the same time are. So let's see, the second toss is heads and there are exactly 2 consecutive heads. So right here, the second toss is heads, so this works. The second toss is heads and there's exactly 2. What else do we have? That has the second toss is heads, but there's not exactly 2. This one has a second toss is heads, but there's not exactly 2 of them. This one has that there's the second toss is heads and there's exactly 2 of them. So that means there's 2 out of 8. Okay, that simplifies to 1/4, which equals 1 times 1 and 2 times 4, which is 8. So I have that 1/4, sorry. So I have that 1/4 equals 1/8, which is not correct. So not correct, which means if it's not correct, then these are dependent events. Okay, and dependent means that they depend on one another, which again should make sense because if you look at these, the only way that you can get 2 consecutive heads is if the second toss is heads, because there's only 3, right? You can't get 2 consecutive heads if the middle toss is not a heads. So, okay, but then you need the algebra to support it. So there you go. All right, so then that brings us to our last page. All right, let's see. Ben owns a delicatessen. He collected data on sales of his most popular sandwiches for 1 week and recorded them in the table below. Here. So bread choices. We have country white bread, whole wheat bread, and sourdough bread. The sandwich choices are Ben's Club, Turkey Melt, Roasted Chicken, Veggie Delight, and then we have totals here. If you remember back in Math 1, this is a two-way frequency table. I'm just going to write it here. So this is a two-way frequency table, which you guys talked about last year in your stats unit. This is a two-way frequency unit because it's talking about 2 things, the sandwich choice and the bread choice. Okay, and we'll use these pretty frequently in this unit. Okay, so go ahead and take your calculators and calculate how many Ben's Club sandwiches there are: turkey melt, roasted chicken, veggie delight, and then how many sandwiches are made on country white, whole wheat, and sourdough. Okay, go ahead and pause and do that. Okay, so let's check your work. This is called your marginal frequency. If you remember back to last year, marginal frequency is the total of a row or column. So Ben's Club has 92. Turkey melts, there's 80. Roasted chicken, there's 75. Veggie delight, there's 73. And then be very careful how you're putting these in. These numbers are going to influence our next problems. Sandwiches made on country white, there were 102. Sandwiches made on whole wheat, there were 112. Sandwiches made on sourdough, there were 106. If you add up the totals for the row and for the column, you should get 320. That's a good way to check your work. If you don't get the same thing left to right and up to down, then you definitely made a mistake. Okay, you will always get the same thing. So 320. Okay. It says each of the following statements describes a pair of events. For each statement, determine if the events seem to be independent. Seem to be. I'll talk about why it says seem to be. Based on the data in the table, and write an explanation. All right. In order to determine if the events are independent, we want to know if that formula is true or not. So it says a random customer orders Ben's Club sandwich on country white bread. So we want to know if the probability of Ben's Club and country white is equal to the probability of Ben's Club times the probability of country white. Okay, so again, we want to know if this is true. If it is, they're independent events. If it's not true, then they're dependent on one another. Okay, so the nice part about a table is you don't really have to do what we did with the last one where you have to create a sample space and go find it. It's just totals in here, which is nice. Okay, so the probability of Ben's Club and country white means that we're doing Ben's Club and country white. Actually, I'm going to use a highlighter. It's a little bit easier for you guys to see. So it means that I would be saying here's Ben's Club and here's country white. Okay. Notice that Ben's Club and country white intersect at this 44 right here. So that means that the probability of both of those happening would be 44 out of my total of 320. So out of the 320 possibilities, 44 of them have both. What is the probability of Ben's Club? Well, that would be the total for Ben's Club, which would be 92 out of 320. And then times, what is the probability of country white? That would be all the way here of 102 out of 320. And you can see now why these totals are so important. Okay, so we're going to convert these into percentages. If you remember at the beginning of the notes, I said to you that there's a 1% leeway. Okay, and I'll explain why. Let's go to my calculator here. All right, so we're going to put this into our calculator. So go ahead and put 44 divided by 320. Let me get this. So I get 0.1375. Calculator keeps disappearing. Hold on. All right, and then I'm going to put in parentheses 92 divided by 320 times 102 divided by 320. And I get that this is equal to 0.09. And we're going to take 4 decimal places here, 16. And the reason that we're taking 4, not 2, is because I'm going to convert these into percentages. So this is about 13, well, this one's actually exact. This one's 13.75%. And then this one would be about 9.16%. Okay, in order for them to be, obviously they're not equal, but because this is a bigger sample size, we use the within 1%. So that was that within 1% leeway. So within 1%. You have to do this anytime you have a big population. Anytime that you do dice and all that stuff, it's always going to be exact. But anytime you have this, there's always going to be like a little bit of leeway. And every book kind of defines it as differently of what we consider close enough or not close enough. And we're always going to use within 1%. Changing these in a percentage makes it a lot easier, but we need to make sure we use 2 decimal places. Otherwise, sometimes rounding will actually affect our answer. Okay, so 13.75% is not within 1% of 9.16%. So these are not equal. Okay, so that means that these are dependent. Remember, our formula is checking for independence. Since it's not true, these are dependent events. Okay, that means that these two events are dependent on one another. This is the type of explanation then that you would be expected to write. I'm going to scroll down. So again, they're dependent. So a person ordering Ben's club sandwich does have an effect on the chance that they order country white bread. So go ahead and fill this in. Pause it, write it down. Okay, so dependent means that there is an effect. So if a person orders Ben's club sandwich, there's a really good likelihood that it is going to affect the chance that they order country white bread. This would be the type of explanation that you're going to see in the next one that I'll kind of word it the same way. Wording of these types of explanations is really important. It shows that you truly understand what it means to be independent versus dependent. But sometimes it can be tricky on how it's worded, and I will be grading you on how you word these. Okay, really, you're just really looking for that does or does not have an effect. Okay, so let's try the next one. Let's see over here. This over here. We have a random customer orders the roasted chicken sandwich on whole wheat bread. So we want to know if the probability, let's see, roasted chicken and whole wheat. We want to know if that equals the probability of roasted chicken times the probability of whole wheat. Okay, so I'm going to move these highlights. So I'm going to move this. Oops. I'm going to move this highlight to roasted chicken. Should be right here. And whole wheat, which is where here. Come on. Whole wheat. Oh my goodness. Sorry, I don't know what's going on right now. Come on. I'm gonna move this to roasted chicken. Okay, so by looking at these two columns, I can see that the probability of roasted chicken and whole wheat is their intersection, which is at 26 right here. So 26 out of 320. The probability of roasted chicken is this entire column, which is 75 out of 320. And then times whole wheat would be this entire row, which is 112 out of 320. And the nice part is that the numbers are all right there for you. All right, so let's take our calculator. Now we're going to figure out these percentages. Okay, so 26 divided by 320, and then 75 out of 320. Oops. 320 times 112 divided by 320. All right. So the 26 out of 320, again, 4 decimal places here. So it's going to be 0.0813. 0.0813 equals 0.0820. So that means that this is about 8.13%. And I would change it to percentages. It always makes it easier to see if it's within 1%. And 8.20%. And I can see that these are within 1% of each other. They're actually really, really close to each other. So that means that these are independent events. So independent events. So there's a lot of work you need to do for these problems. You need to show the algebra. You need to state whether it's independent or dependent, and then you're going to need an explanation for each. So they do take a little bit of time, but you're going to look for all three of those. So the algebra, the statement. Sometimes we gloss over the statement. We never actually state what they are. And then three is going to be what your explanation is. Okay. So remember, independent events means that one event does not affect the other. So that means that roasted chicken does not affect the fact that they will get a whole wheat bread. They could pick any of the three. This would be an explanation of those independent events. A person ordering roasted chicken does not have an effect on the chance they order. Oops, cut this off. On the chance that they order on whole wheat bread. So a person ordering roasted chicken does not have an effect on the chance that they order on whole wheat bread. I'm going to take this calculator out of here. Okay. Notice the fact that one does have an effect, does not have an effect. I mean, that's really the big difference. Otherwise, it's just talking about the two events. We have roasted chicken, we have whole wheat bread, and in the middle, does not affect. Okay, meaning again that they could order roasted chicken, the chance of them having whole wheat bread is not dependent on what they order. Okay, there's one thing I want you to change in your homework before you shut this off. So you're going to grab worksheet number 4 from the sub. On the bottom here at number 2, it says, suppose that a married couple will have 3 children, and suppose that having a boy or girl is equally likely each time. Consider the following events. This should say like example 3 in the notes, not 2. This is just like flipping a coin, because flipping a coin 3 times, that was 3. Flipping a coin 3 times is heads or tails. If you have 3 children and it's just as likely that you have a girl or a boy, then that would be the same thing, like heads, tails, boy, girl. So you would literally just go through and go, okay, it's going to be a boy, 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 or a boy, boy, girl, or a boy, girl, boy, or a boy, girl, girl. And then you're going to do the same thing for girl, and you're going to notice that there's going to be the same 8 outcomes. Just instead of an H and a T, it's going to be a B and a G. And then you're going to answer those questions based off of these 3 events. Okay, and then last thing, this table looks a little bit more confusing than it is. You want to determine if the events are independent. Okay, independent means that this probability is 0.028. You want to know if it equals the probability of event A times the probability of event B. Okay, that is your big formula. The probability of A and B equals the probability of A times the probability of B. So if you're determining independence, you want to know if that's true. Here's A and B. Here's A times B. So is this true? You're going to choose your calculator. Okay? I will be back tomorrow. If you have any questions, come see me in the morning. Thank you.